Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you look up at the Andromeda galaxy tonight, you're actually looking at a completely incomplete map.
Yeah, totally incomplete. We miss so much of what's actually there.
Right. Because just recently, on March 30th, 2026, astronomers announced this incredible update to our cosmic backyard.
It's honestly one of the most fascinating finds in recent years.
It really is. They found an entirely new galaxy hiding right there, orbiting Andromeda. Not, billions of light years away at the edge of the universe, but literally right next door.
And the kicker is our billion-dollar supercomputers and all those advanced algorithms. They entirely missed it.
Which is wild. But before we get into that, new galaxy is a phrase we need to handle carefully, right?
Oh, absolutely. When people hear new galaxy, it immediately brings to mind like sweeping spiral arms, glowing pink nebulas, supermassive black holes.
Like the classic Hubble desktop backgrounds.
Exactly. But this newly discovered object, officially designated Andromeda XXXVI, or NXXVI for short, is the absolute antithesis of that majestic imagery.
So what are we actually looking at here?
Well, we classify it as an ultra-faint dwarf galaxy, a UFD. It's a tiny, incredibly elusive, and just profoundly ancient system.
Right. It's less of a shiny metropolis and more of a cosmic ghost wandering through Andromeda's halo.
A ghost is the perfect way to describe it. And we aren't just going to list off coordinates for a new speck in the sky today.
No, because the reason this faint little ghost matters to you listening right now is that it's essentially a cosmic time machine.
Yeah, it operates as this pristine, untouched laboratory for the universe's most mysterious substance, which is dark matter.
And understanding how it was found requires looking at the sheer power of the human eye, even in an era totally dominated by artificial intelligence.
What makes an object so small, capable of answering the biggest questions in physics, is its extreme nature. Its tiny size and profound faintness hold the real secrets.
Because massive galaxies are just too chaotic, right?
Exactly. They're noisy.
Yeah.
But tiny dead systems like this one offer a completely clean environment to observe fundamental physics at work.
Okay, so let's figure out what it actually means to be an ultra-faint dwarf galaxy. Just how small and how dim does a collection of stars have to be to get that classification?
Well, geographically speaking, and XXXVI sits about 2.53 million light years away from Earth.
Which puts it squarely in the local group, our neighborhood.
Right. But the really vital measurement is its distance from the center of the Andromeda galaxy itself, which clocks in at roughly 388,000 light years.
That sounds like a massive distance. That's farther than the moon is from the Earth if you scale it up to galactic proportions.
It does sound distant, but in galactic physics, it sits deep within Andromeda's gravitational grip. Astrophysicists use this metric called the virial radius.
The virial radius? Okay, break that down for us.
You can think of the virial radius as the ultimate boundary line of a galaxy's gravitational dominance.
So it's like the city limits of its gravity.
Yeah, exactly. It's the sphere of influence where the larger galaxy's gravity dictates the motion of everything inside it, rather than the expansion of the universe pulling things apart.
And what's the virial radius for a giant spiral like Andromeda?
For Andromeda, that radius extends outward to roughly 850,000 light years.
Oh, wow. So at 388,000 light years. And XXXVI is well within the city limits.
Firmly within the suburbs, yeah. It is securely and permanently a gravitationally bound satellite of Andromeda.
It's just orbiting the larger galaxy, locked in this cosmic band, governed entirely by Andromeda's immense mass.
Exactly. So it's locked in, but the sheer compactness of this object is what really duns the mind.
Yeah, the measurements show it has a half-light radius of just 208 light years.
Which is incredibly tiny.
Our Milky Way is roughly 100,000 light years across. This entire new galaxy is just a couple of hundred light years wide.
Barely a blip.
I do need to stop right there, though, because half-light radius is sort of a weird term. Why don't astronomers just measure from the center to the edge?
Well, because galaxies do not have hard, sharp edges like a planet or, a table.
Right, they kind of just fade out.
Yeah, they're diffuse clouds of stars that gradually thin out into nothingness.
Yeah.
If you try to measure to the absolute outermost star, you get wildly inconsistent results.
Because it just depends on how sensitive your telescope is. Right?
Precisely. Instead, astronomers use the half-light radius. It's the distance from the core within which exactly 50% of the galaxy's total light is emitted.
Got it. So it provides a robust, mathematically consistent way to define the bulk of this fuzzy, edgeless object.
Exactly. So the core, the main glowing heart of this thing, is only 208 light years across. That's about 64 parsecs.
And I was reading that its structure is unusually uniform, too.
It is. We measure the shape of these objects using ellipticity. A perfect circle has an ellipticity of 0.
And a highly stretched, cigar-like oval would be closer to 1.
Right, and XXXVI has an ellipticity of about 0.015.
So it's virtually a perfect sphere.
It is remarkably spherical. It makes it potentially the second most compact, ultra-faint dwarf satellite ever found orbiting Andromeda.
Wow. And then we get to the brightness, or I guess the complete lack of brightness.
Yeah, it's staggeringly dim.
The data gives it an absolute visual magnitude of roughly -6.0. And the astronomical magnitude scale is notoriously counterintuitive.
Oh, it's totally backwards.
The lower or more negative the number, the brighter the object, right? Our sun sits at around -26.
And the full moon is around -13.
So a whole galaxy sitting at -6 is just profoundly dim. It's like a single dimly lit neighborhood out in the countryside trying to be seen next to the glaring neon lights of a megacity.
And that megacity being Andromeda, that visual illustrates the detection problem perfectly, honestly.
Because its intrinsic light is just entirely washed out by the larger galaxy.
Washed out by the glare and the vast distances involved, it barely registers against the background static of the cosmos.
But wait, if it is so incredibly small, just 200-something light years across and unfathomably dim, why are we even classifying this as a galaxy?
That's a great question.
Because there are globular clusters out there, these tight spheres of thousands of stars that are way brighter and denser than this. Why does an XXXVI get the prestigious title of galaxy instead of just being a random rogue star cluster?
The distinction between a star cluster and a dwarf galaxy is one of the most crucial concepts in modern astronomy. And it actually has nothing to do with size or star count.
Oh, really? What does it come down to then?
It comes down to invisible mass. A globular cluster is a collection of stars, gas, and dust held together exclusively by their own mutual gravity.
So what you see is what you get.
Exactly. If you add up the mass of all the glowing stars in a globular cluster, it perfectly accounts for the gravitational glue holding the whole structure together.
No hidden variables.
None at all. But a galaxy, even an ultra-faint dwarf like XXXVI, is fundamentally dark matter dominated.
Okay, so it's essentially a massive, invisible halo of dark matter that just happens to have a few stars sprinkled in the very center of it.
That's exactly it. The stars are merely the glowing paint on a much larger, invisible structural foundation.
That's wild. So when astronomers analyze the dynamics of these objects, the visible matter is basically negligible.
Completely negligible. Without a massive dark matter halo, the galaxy would simply fly apart. That halo is the defining signature. If it has a halo, it's a galaxy.
So its dimness isn't a sign that it failed at being a galaxy. It's not like a star cluster that just gave up.
No, not at all. The dimness is an artifact of extreme age, which really brings us to the origins of this object.
Right, because we aren't looking at a dynamic, evolving system here. We are looking at a fossil.
A literal cosmic fossil. The estimated age of the stars in XXXVI and XXXVI is roughly 12.5 billion years.
The universe itself is only 13.8 billion years old, so the stars in this tiny smudge formed shortly after the Big Bang itself.
They were among the very first generations of stars to light up the cosmos.
So what happened to it? Why did it stop growing?
Systems of this nature are referred to as reionization fossils. To grasp the mechanics of that, you have to picture the universe during its infancy.
Okay, setting the scene.
For several hundred million years following the Big Bang, the universe was filled with this thick, obscuring fog of neutral hydrogen gas.
Like a literal fog.
Essentially, yeah. Light could not travel freely. The cosmos was opaque. Astronomers call this period the Dark Ages.
It was just a giant soup of hydrogen waiting for something to happen.
Then, the first stars and the first primitive galaxies ignited. And these early stars were monstrously massive, incredibly hot.
And they must have pumped out staggering amounts of radiation.
There's huge amounts of ultraviolet radiation. This intense UV radiation literally tore the electrons away from the neutral hydrogen atoms in the surrounding space.
And that process is what we call reionization.
Exactly. It burned away the fog, making the universe transparent. But this epoch was exceptionally violent.
Violent how? Like, if I'm this little forming dwarf galaxy gathering my own hydrogen to make my own stars, What does that UV wave actually do to me?
Well, for a delicate system with a weak gravitational well like in XXXVI, that wave of intense radiation was absolutely devastating.
Because it heated up the gas.
Right. The intense UV light heated the gas inside these small dark matter halos, and when a gas heats up, its particles move faster.
Oh, I see. So the thermal kinetic energy of the gas rapidly exceeded the escape velocity of the tiny galaxy's gravity.
Exactly. The gas expanded and literally boiled away into deep space.
It just got blasted dry by the bigger galaxies turning their lights on. And without cold, dense gas, a galaxy cannot form new stars.
The factory gets permanently shut down. The initial burst of star formation is abruptly quenched.
Wow. And we can verify this quenching by looking at the galaxy's chemical signature, right?
We can. Specifically, we look at its metallicity. The spectroscopic data for XXES shows a metallicity of roughly -2.5.
I actually need to translate an astronomical quirk for everyone listening here, because metallicity in astronomy doesn't mean what it means in chemistry class.
No, it definitely doesn't.
To an astronomer, anything heavier than hydrogen and helium is considered a metal. Like oxygen, carbon, nitrogen, those are all metals in this context.
It's a funny historical artifact in the terminology, but the physics it describes tells a vital story about the universe.
Because the Big Bang essentially produced only hydrogen, helium, and a microscopic trace of lithium, right?
Right. All the heavier elements, these astronomical metals, were forged much later.
They were crushed together inside the extreme heat and pressure of stellar cores.
And then distributed across the universe when those stars died in supernova explosions.
So the very first stars to ever exist in the universe were made of pure hydrogen and helium. They had a metallicity of basically 0.
Correct. When those first-generation stars exploded, they seeded the surrounding gas clouds with the newly forged, heavier elements.
So the second generation of stars formed from that slightly polluted gas, making their metallicity slightly higher.
Exactly. The more generations of stars a galaxy produces, the more metal-rich its gas becomes.
I mean, our sun is a relatively modern star, forming only about 4.6 billion years ago.
And so it has a high metallicity because it formed from gas enriched by countless generations of dead stars over billions of years.
And X-Pite has an incredibly low metallicity of -2.5. It's chemically pristine.
It barely has any heavy elements at all. It is absolute chemical confirmation that there has been no recent star formation there.
It is a completely unevolved system.
Totally. It birthed its initial crop of stars roughly 12.5 billion years ago. The process of reionization boiled away the rest of its fuel, and then it simply stopped.
It's really like finding a perfectly preserved Roman ruin.
That's a great analogy.
Imagine uncovering a massive ancient city, but it was suddenly abandoned just a few decades after it was built, and nobody ever came back. It was never built over.
You can see the original stones exactly as they were laid.
Right. Whereas massive galaxies like our Milky Way or Andromeda are like modern, sprawling cities. They are built on top of countless layers of demolition and new construction.
Paving over the old, mixing all the materials together. You can't easily see the ancient history because there's a skyscraper on top of it.
But the undisturbed nature of XXXVI is what makes it so incredibly valuable.
Yes, because it lost its original gas, perhaps from that early universe reionization, or potentially due to brutal tidal interactions with Andromeda itself.
Oh, like Andromeda's immense gravity physically stripping the gas away as the dwarf galaxy orbits.
Exactly. Regardless of the exact mechanism of gas loss, its development was just frozen in time.
And because it lost its gas so early, it never formed enough stars to be bright. Which brings us to the profound dimness and the story of how we actually found it, which is just ridiculous.
It's an amazing story.
We have this phenomenally dim, incredibly tiny, 12.5 billion-year-old ghost floating in the massive glare of Andromeda, barely emitting any light at all. How do you even find that?
The discovery process highlights this fascinating intersection between massive astronomical survey data and pure human intuition.
So where did the initial data come from?
The foundational data came from the Pan-Andromeda Archaeological Survey, or PANDAS. This was a sweeping, deep imaging campaign utilizing the Canada-France-Hawaii telescope.
Right, and the goal there was to map the extended halo of Andromeda, essentially looking deep into the galactic suburbs.
Deep imaging surveys like PANDAS operate by taking incredibly long exposure photographs of the exact same patches of sky.
Just staring at the dark.
Yes, and then stacking those images to capture the absolute faintest possible photons. They generate an incomprehensible amount of data.
Terabytes and terabytes of wide-field images capturing millions of faint points of light. It's a digital haystack of cosmic proportions.
And this is where the story gets wonderfully human. Because the person who found this wasn't an algorithm, and it wasn't a team of postdocs in a supercomputing lab.
It was an amateur astronomer, right? Giuseppe Donasiello.
Yes. Despite all our advanced technology, Donasiello found this galaxy through systematic visual inspection of the PANDAS footprint.
He literally just sat there, looked closely at the images, and spotted an incredibly subtle overdensity of stars.
Donasiello has a famously keen eye for spotting these structures, actually. He has contributed to several previous dwarf galaxy discoveries.
Out in the outskirts of Andromeda and other nearby groups, right?
Yeah. He possesses this unique visual acuity for identifying faint, diffuse, stellar associations that just blend into the background for anyone else.
But of course, science requires verification. An amateur spotting a smudge on a monitor is the spark, but the professionals have to move in to prove it's actually a galaxy.
Definitely. The professional follow-up was spearheaded by Joanna D. Sikowska from the Institute of Astrophysics of Andalusia.
And they needed immense light-gathering power to prove this wasn't an optical artifact or just a random clustering of foreground Milky Way stars.
So they utilized the OSIRIS+ instrument, which is mounted on the Gran Telescopio Canarias in La Palma.
That's a 10.4-meter telescope. That is serious heavy artillery.
It is one of the premier optical and infrared telescopes on the planet. Its massive mirror was absolutely necessary to capture enough light to resolve the individual stars within this faint smudge.
So they aren't just looking at a blurry blob anymore. They are separating the blob into its constituent individual suns.
Exactly. And by doing so, they constructed a color magnitude diagram, or CMD.
I really want to break down what a color magnitude diagram actually is because it sounds intimidating, but it is one of the coolest diagnostic tools in astronomy.
It's foundational to our understanding of stars.
Imagine taking every individual star that the 10.4-meter telescope resolved in that smudge and plotting it on a graph. The vertical axis is its magnitude or how bright it is.
And the horizontal axis is its color, which tells you its temperature.
Right. Blue stars are brutally hot, red stars are cooler.
And stars do not scatter randomly on this graph. Because the laws of stellar physics govern exactly how stars burn hydrogen, a group of stars born at the same time will align along very specific, predictable curves.
Right, because they all form from the same cloud of gas.
Exactly. The most massive, blue, hot stars burn through their fuel incredibly fast and die young.
While the smaller, cooler red stars burn their fuel slowly over hundreds of billions of years.
So by looking at which stars are still burning and which are missing from that curve, you can tell exactly how old the whole group is.
That is such a brilliant mechanism.
It is. By plotting the resolved stars from the Gran Telescopio Canarias, the team identified the unmistakable shape of an ancient, metal-poor stellar population.
They found the main sequence turnoff point.
Yes, the exact spot on the graph where stars of a certain mass are currently exhausting their hydrogen cores.
And that turnoff point acts like a cosmic clock, providing that 12.5 billion year age estimate we talked about.
Exactly. The stacked images also revealed a clear overdensity of these specific ancient stars, perfectly nestled between two incredibly bright foreground stars.
Oh, those foreground stars are in our own Milky Way, right? Physically in the way, just photobombing the image of the distant dwarf galaxy.
They really are. But the data was definitive. This was a distinct galactic structure.
But wait, let's be real here. It is 2026. We live in an era of massive computing power and highly advanced machine learning.
We do.
Why on earth are we relying on a guy looking at a computer monitor to find this? Shouldn't a trained algorithm have flagged this instant anomaly the millisecond the PANDAS data was uploaded?
You'd think so. But the limits of our automated detection systems are really exposed in these extreme low surface brightness regimes.
How so?
While machine learning algorithms are phenomenally powerful at recognizing patterns they have been explicitly trained to detect, and they are ruthlessly efficient at filtering out noise.
But an ultra-faint dwarf galaxy like an XXXVI operates right at the absolute threshold of detectability.
The signal-to-noise ratio is just terrible. It is almost entirely noise.
So to an algorithm, it just looks like junk data.
Basically. To a machine learning algorithm searching for statistically significant clusters, a few dozen faint, spread out stars scattered among tens of thousands of bright foreground stars registers as a minor random fluctuation.
Just background static. So the algorithm smooths it out or ignores it entirely.
Exactly. And if you tune the algorithms to be sensitive enough to flag and XXXVI automatically, They would also generate tens of thousands of false positives.
Oh, I see. Every random clump of 3 stars would trigger an alert. The algorithm is too rigid. It lacks that subjective gut feeling of human intuition.
Right. The human visual cortex evolved as an exquisite pattern recognition engine. We are biologically tuned to notice subtle anomalies in texture and structure.
Even when the data is incredibly messy.
Exactly. Human insight remains highly complementary to machine learning. The algorithm dismisses the faint whisper of a galaxy as an artifact or pixel noise.
But a dedicated human observer like Donatello looks at the exact same pixels and recognizes a cohesive shape.
The machines gather the light from 2.5 million light years away, but it takes a human mind to actually recognize the ghost hidden inside the data.
That's incredible. And cataloging these ghosts is critical because finding them solves one of the most frustrating, glaring mysteries in modern astrophysics, right?
Oh, absolutely. It directly addresses the missing satellite problem.
The missing satellite problem. Let's scale this up from one tiny galaxy to the architecture of the entire universe.
It's a problem that has been a thorn in the side of theoretical astrophysics for decades. It fundamentally challenges our standard cosmological model.
So our current understanding of the universe relies on a framework called cold dark matter.
Right. And when astrophysicists run massive, complex supercomputer simulations known as N-body simulations, they model how the universe evolved.
Going from a relatively smooth state shortly after the Big Bang into the massive cosmic web of galaxies we see today.
And in these simulations, dark matter acts as the gravitational scaffolding.
The dark matter clumps together first because it only interacts via gravity. It doesn't bounce off itself or emit light. It just gathers into these massive invisible blobs.
We call those blobs dark matter halos. Once a massive halo forms, its immense gravity pulls in the ordinary matter, the hydrogen and helium gas.
And that gas falls into the center of the dark matter, compresses and ignites into a galaxy.
It's exactly. But the high-resolution supercomputer simulations reveal a critical detail. A massive dark matter halo, like the one surrounding the Milky Way, or Andromeda, shouldn't be a single, smooth sphere.
It should be highly substructured, right?
Yes. It should be swarming with thousands of smaller, independent dark matter subhalos orbiting within and around it.
And if the math says those thousands of dark matter subhalos exist, they should have pulled in their own gas to form thousands of small dwarf galaxies.
That's the logical conclusion. The Milky Way and Andromeda should look like massive, glowing cities surrounded by thousands of smaller satellite towns.
But when astronomers actually pointed their telescopes at the sky, they didn't see thousands of satellite galaxies.
Not even close. For a long time, we only saw a few dozen around the Milky Way, and even fewer around Andromeda.
That is a massive, glaring discrepancy. The computer simulations predict thousands of satellites, and the actual observations show a mere handful.
And that is the missing satellite problem.
It sounds like a crisis in the making. I mean, if the math says there should be thousands and the telescopes only see 20, either the math is wrong or the telescopes are blind.
Exactly. It suggested that either our fundamental theories of cold dark matter were completely flawed, or there was a physical mechanism preventing us from detecting the vast majority of these galaxies.
And the discovery of Andromeda 6, along with a recent surge of similar discoveries, proves that the latter is true.
By pushing the limits of our observational thresholds to find extremely faint, diffuse objects, we are slowly closing the gap between simulation and reality.
We are finding the missing satellites. They weren't missing, they were just incredibly dark.
Right. Andromeda is now estimated to host nearly 100 dwarf satellites, with roughly half of them firmly confirmed through follow-up observations.
Discoveries like NXX6, along with other recent finds like NXXV and Pegasus V, also known as NXX4.
They are populating the extreme faint end of the luminosity function. We are proving that these smaller dark matter subhalos do exist, and they do contain stellar populations.
They are simply operating at the very edge of what our current technology can perceive.
Exactly. But what gets really interesting is comparing the satellite galaxies around Andromeda to the ones orbiting our own Milky Way.
You'd think they would be identical, honestly. Two massive spiral galaxies should have similar cosmic suburbs.
You would think so, but they actually exhibit fascinating differences. When we compare the ultra-faint dwarf populations, Andromeda's UFDs frequently exhibit much more extended star formation histories.
Really?
Yeah, and a wider spread of metallicity than their Milky Way counterparts, even when comparing galaxies of identical total mass.
What is the mechanism behind that? Why would a dwarf galaxy around Andromeda keep making stars longer than a dwarf galaxy around the Milky Way?
It points toward the different accretion histories and environmental factors of the two host galaxies.
Because the Milky Way and Andromeda built up their massive bulk over billions of years by cannibalizing smaller galaxies.
Right. It is possible that the specific orbital dynamics or the density of the circumgalactic medium around Andromeda allowed some of these incoming dwarfs to hold on to their cold gas reservoirs slightly longer.
So before the ram pressure or tidal forces totally stripped it away, they got a little extra time.
Exactly. Holding on to that gas for an extra few 100 million years allows for multiple subsequent generations of star formation.
Which enriches the gas and creates that wider metallicity spread we observe. That's amazing.
It provides subtle clues about the divergent evolutionary paths of these two giant spirals.
We are literally slowly fleshing out this invisible dark matter map. But NX XXXVI offers us something uniquely powerful.
Because it's so compact.
Right, just 208 light years across, it sits in one of the absolute smallest dark matter halos, mathematically capable of holding onto enough gas to form stars.
It is the extreme lower limit of galaxy formation. It represents the absolute threshold.
Meaning any dark matter halo smaller than XXXVI simply doesn't have the gravitational depth to capture gas. The gas just drifts right past it.
Therefore, studying NX work is studying the smallest possible unit of galactic dark matter.
But I need to challenge this whole concept for a second. We constantly talk about dark matter as this invisible theoretical substance.
It's tricky to conceptualize. Yeah?
It doesn't emit light, it doesn't reflect light, it doesn't block light, it doesn't interact with electromagnetism whatsoever.
Yeah.
So how can looking at a couple hundred incredibly slow, ancient, faint stars in XXXVI actually allow an astrophysicist to measure something that is fundamentally invisible?
Consider this analogy. It's like watching a handful of autumn leaves caught in an invisible tornado.
Okay, I like that. You absolutely cannot see the wind. The wind is completely transparent.
But if you watch the leaves and you measure exactly how fast they are swirling around, the speed of those leaves tells you exactly how much force the invisible wind must be exerting.
Oh, that makes perfect sense. The physics translates perfectly.
The leaves are the ancient visible stars in XXXVI, and the invisible tornado is the massive gravitational well of the dark matter halo.
So astrophysicists measure the invisible wind through a technique called stellar kinematics.
Specifically, calculating the internal velocity dispersion of the stars.
You literally measure how fast the stars are buzzing around inside the galaxy.
Even though the dwarf galaxy appears static and frozen in a photograph, those individual stars are moving rapidly. By employing high-resolution spectroscopy, astronomers analyze the light from individual stars.
They're looking for minute Doppler shifts in the absorption lines of the star's spectrum, right?
Exactly. If a star is moving slightly toward our telescope, the light waves are compressed and the spectrum shifts slightly toward the blue end.
And if the star is moving away from us in its orbit, the light waves are stretched and the spectrum shifts toward the red end.
Perfect. So by measuring those red and blue shifts, you get the precise speed of the star relative to us. We map the speeds of dozens of stars within the dwarf galaxy.
Now, if an XXXVI was only held together by the weak gravity of its sparse visible stars, those stars would have to be moving very slowly, wouldn't they?
Extremely slowly. If they moved fast, the weak gravity of the visible matter wouldn't be strong enough to hold them.
And they would simply fly off into deep space, totally dissipating the cluster.
However, what observational data consistently reveals with these ultra-faint dwarfs is that the stars are moving much, much faster than the visible mass allows.
The leaves are swirling at hurricane speed.
Yes, which proves there is a massive invisible wind, a huge source of unseen gravity holding them locked in that tight little 200 light-year sphere.
So the velocity dispersion, the statistical spread of all those varying stellar speeds, provides a direct mathematical measurement of the total gravitational mass present.
You subtract the visible mass of the stars, and the remainder is the mass of the dark matter halo.
And because XXXVI is so tiny and incredibly compact, that immense amount of dark matter is packed into a very small, dense volume.
This is where we get to actually put competing models of theoretical physics to the test, because not all dark matter theories are identical.
Right. The standard cosmological model relies on cold dark matter. And in this context, cold means the theoretical dark matter particles move sluggishly compared to the speed of light.
Exactly. And because they move slowly, they easily clump together into very tight, dense, small structures.
Like the halo hosting and XXXVI.
But there are competing models attempting to solve other cosmic anomalies. There's warm dark matter, where the theoretical particles move much faster.
The higher kinetic energy of warm dark matter would smooth out small-scale gravitational structures, making it incredibly difficult to form tiny, dense halos.
Right, so if dark matter was warm, an XE6 physically couldn't exist.
Because the fast-moving dark matter particles would never clump tightly enough to pull in the gas to make those first stars.
Precisely why finding these extreme microgalaxies is so absolutely vital.
Are there any other theories?
There is also the theory of self-interacting dark matter, which proposes that dark matter particles don't just pass through each other like ghosts.
But they actually bounce off one another in the dense centers of halos.
Yes. This scattering effect would fundamentally alter the density profile of the halo, making the core less dense than standard cold dark matter predicts.
Wow. So by measuring the exact speed of the leaves in this one specific tiny tornado, astrophysicists can reverse engineer the fundamental particle physics of the invisible wind.
It's all connected. If the dark matter is cold and clumpy, the stars will orbit with a specific velocity profile.
And if the dark matter particles are bouncing off each other, the internal gravity changes and the stars will move differently.
Exactly. This tiny, faint smudge, spotted by a guy looking at a computer screen, provides the exact raw data that theoretical physicists need.
They need it to either validate or completely rewrite our fundamental understanding of the universe's most abundant substance.
It illustrates the profound interconnectedness of modern astrophysics. You cannot decipher the microscopic quantum nature of a dark matter particle without observing the macroscopic gravitational dynamics of the faintest, oldest galaxies in the universe.
The subatomic and the cosmic scales are inexorably linked.
They really are.
We started by looking up at Andromeda, this familiar, mapped-out neighbor in the night sky. But hidden within the immense glare of its billions of stars, we found Andromeda XXXVI.
A 12.5 billion-year-old collection of chemically pristine stars.
A pristine Roman ruin of a galaxy whose ability to grow, evolve, and shine was brutally quenched by the ferocious, stripping radiation of the early universe's first light.
A structure so faint and so diffuse that the most advanced automated supercomputers and machine learning algorithms swept right past it,
mathematically dismissing it as background noise. It required the dedication, patience, and exquisite biological pattern recognition of a human being to pull its signal out of the shadows.
And from that human discovery, confirmed by aiming a 10.4-meter mirror at the sky to dissect its individual suns, we are granted a profound new laboratory.
A tiny, 208 light-year-wide bubble of intense dark matter that helps solve the missing satellite problem.
It proves the math of the universe right, while providing the exact kind of extreme high-density environment physicists need to test the fundamental laws of reality.
It is a staggering cascade of scientific knowledge generated from a single, barely perceptible smudge.
And as we push our observational capabilities further, we are going to find many more of them.
Especially as deeper imaging surveys come online, right?
Oh, absolutely. As we continually utilize the phenomenal resolving power of instruments like the James Webb Space Telescope and Hubble, we will peel back more layers of this cosmic ecosystem.
We will inevitably map dozens, perhaps hundreds more of these ultra-faint satellites hidden in the halos of both Andromeda and the Milky Way.
We are mapping the true underlying invisible architecture of the local group. These tiny systems aren't just anomalies or astronomical curiosities.
They are the fundamental building blocks of cosmic structure. The massive, majestic spiral galaxies we see today were literally constructed by cannibalizing and merging thousands of these tiny, ancient systems over billions of years.
Objects like ENS XT66 are the rare survivors.
They are the few that managed to avoid being entirely consumed, left to orbit in the dark suburbs for over 12 billion years, preserving the chemical and physical conditions of the universe's dawn.
It fundamentally changes how you perceive the universe.
It really does. I want to leave you with a final thought, something to mull over the next time you step outside on a clear night. When you look up, your eyes are naturally, inevitably drawn to the bright things.
The shining stars, the glowing planets.
The sweeping arm of the Milky Way itself. We are biologically and culturally conditioned to think that the light is where the action is, that the glowing points are where the universe happens.
But the story of Andromeda XXXVI suggests something far more profound.
It suggests that the empty, seemingly black spaces between those bright stars aren't empty at all. They are secretly teeming with ancient, invisible ghosts, vast, dark matter-dominated relics holding the pristine secrets of the universe's very first billion years. They are out there right now, quietly guarding the history of the cosmos in the dark, just waiting for someone patient enough to look closely.